Hello dear students, I'm Dr. Moin. In this video we are going to discuss about thermo-mechanical analysis TMA, and this is the part 2. In part 1 we have discussed the basic introduction of TMA, then we have seen the history and principle of this technique. We have also seen there the complete instrumentation of thermo-mechanical analysis. So if you didn't watch the part 1 first, I'm providing the link of part 1 in the top right corner, so you can find it in the I button. In this part we are specifically going to discuss the applications of thermo-mechanical analysis. So let's start it. So the first property which we can measure using TMA technique is the coefficient of expansion. The probes and supports used are generally of fused silica. We know that we have already discussed in the instrumentation of TMA that probes are used to exert some force, while supports are used to support the samples. So both of these are used, and these are made up of fused silica. So other materials, so both of these things, probes and supports, are also available in other materials like Pyrex glass, aluminium, epoxy resins, and polypropylene. And why this is preferred in fused silica? Because the coefficient of expansion of this one is very much low in comparison with the most of other materials. For a single material undergoing node transition, the average coefficient of expansion between two temperatures may be measured, which is shown over here in the figure. So here is the TMA curve. So coefficient of expansion of aluminium, which is going to be measured here between 50 and 200 degrees centigrade, and here are the conditions of the whole process. So we can see on the x-axis there is temperature, while y-axis there are dimension. That is what is expansion going to be happen. So with the change in temperature, the dimensions are going to be increased. So we can calculate the average change in expansion between any of the two temperatures. And if we are interested to calculate the instantaneous coefficient of thermal expansion, mean the thermal coefficient expansion at some given point, then we can also calculate that one by calculating the slope from the TMA trace at that point. Another property which can be studied using TMA is glass transition temperature. At the glass transition temperature, the heat capacity and coefficient of expansion change abruptly as shown in the figure. We discuss this right now. Under small load, coefficient of thermal expansion may be measured below and above the glass transition temperature, and the lines extrapolated back to give a single value. So here is the TMA curve. So glass transition temperature by TMA. So we can see that by increase in temperature, so dimension is going to increase, and this increase changes quite abruptly over here. So these both line, if extrapolated, this one towards the back side and this line towards the front side, so both of these lines join at a single point, and that is actually the glass transition temperature. The heating and cooling rates that will affect this temperature, while other factors which may affect this temperature include molecular weight, degree of cure, that is cross-linking, and what are the plasticizer contents, and what is the orientation of our sample. While if a higher force is used, particularly with the penetration probe, then the trace obtained is shown over here. Below glass transition temperature, there is little penetration. We can see over here, we're talking about this. Before glass transition, there is a very small penetration, but above this temperature, the polymer softens and the probe sinks into the material. So definitely above glass transition temperature, the material will be softened and probe will that will sink into the material. So we get this curve. So, and if we extrapolate both of these curves, then they join together at this point, and this is called glass transition temperature. And if we continue heating this material still at higher temperature, then we get the melting point. And at the melting point, there is complete penetration of probe that occurs into our sample. Another property which can be studied with the help of TMA is the solvent swelling of polymers. In this study, the sample and probe are immersed in a suitable solvent. For example, we may have the combination in which suppose we have a copolymer, which is the combination of polystyrene and polybutadiene, and that may be immersed in toluene, which is used here as a solvent. So there will be the gradual uptake of solvent, and that will cause the sample to swell. But there will also be the contamination of that solvent. So we must have to renew our solvent by adding the fresh solvent in it. So here is the TMA curve. We can see here is the swelling of polyisoprene, which is immersed in toluene as a solvent. The atmosphere is static nitrogen and the load is 0.1 Newton. So here we can see the swelling of the rubber, which is going to increase, and that it is going to be the constant with the passage of time. This swelling may be further used to calculate the density of cross-linking by using the Flory-Rehner equation, which is given over here, and that is n is equal to minus natural log of 1 minus v2 plus v2 plus x1 into v2 square over v1 into v2 raised to the power 1 by 3 minus v2 over 2. And what are the parameters inside? So here the small n, what is that? That is actually the cross-linking density, which is calculated in moles per cm cube, while V2 here is the volume fraction of polymer at equilibrium. V1 here in equation, and that represents the molar volume of solvent, and x1 is the polymer solvent interaction parameter. The other factors which can be calculated by using TMA, and they are the expansion, the penetration, and the creep of sample. So all of these properties can be well studied using TMA. So our sample may be in the form of films and fibers, and we may be interested to study the transitions, various transitions in those films and fibers. So samples in the forms of films and fibers can also be studied in TMA. Film samples may be attached by small clamps or clips, and fiber samples by hooks to a special attachment similar to that shown in the figure. So for example, here is the film sample in the form of a thin film that has been introduced over here, and it is grabbed by using clamps. So here is the lower clamp and here is the upper clamp. The sample is generally held under slight tension, and the movement of probe will indicate stretching or shrinkage of the film or fiber. So here the movement of probe, it actually will inform us about the various types of stretching or shrinkage which is going to be happen in our sample, which has been introduced in the form of film or fiber. This is especially useful to show transitions near the glass transition temperature, because the shrinkage or fibers or films it often starts just above glass transition temperature. And why it happens over here? Because the molecular arrangements are more free to alter above glass transition temperature. So here is the TMA curve for nylon fiber, which has been shown over here. So on x-axis there is temperature, while on y-axis there is change in length. So a curve going upward shows the contraction or decrease in length, while a curve going downward shows the extension or increase in length. So the figure shows a nylon fiber which shows slight expansion to glass transition temperature at 20 degrees centigrade. So here at 20 degrees centigrade, which is the glass transition temperature, so it shows quite expansion. But if we see it, then there is a rising curve from here to up to 100 degrees centigrade, which shows that there is contraction or shrinkage which is going to be happen in nylon up to 100 degrees centigrade. And then we observe here a plateau, which is possibly due to moisture loss. And if we continue heating our sample, so again we get the increasing curve, which shows further shrinkage which is going to be happen in our sample. And finally then comes the melting point of our sample, and that is 250 degrees centigrade. By change in temperature, the change of phase is a common phenomena. So these phase transitions can also be studied using TMA. We know that different substances, they exist, they have different polymorphic forms. And these polymorphic forms, they are different from each other by their densities, and they have different from each other due to their coefficient of expansions. And these different forms, these may be detected using the normal expansion probe or a special dilatometric attachment, where the expansion of the sample is transmitted to the probe through an inert packing. So here is the figure, or you can say here is the TMA curve for sulfur, and it has been obtained using the normal probe. So here are the conditions for this one. We know that sulfur has different allotropes like rhombic sulfur or monoclinic sulfur, or these can also be represented as alpha sulfur or beta sulfur, and these are interchangeable to each other at a specific temperature, and that is called transition temperature. So when we increase the temperature, so we can see the curve is quite smooth, and then there is a sudden change. So definitely this is the temperature where one form of sulfur is being converted into other form. So we can say that alpha form is going to be converted into beta form, and at what temperature these forms are going to be converted into each other, that is called transition temperature. So in the case of sulfur, this is 95 degrees centigrade, and if we continue heating the sample further, then ultimately sample will melt and start flowing. The next application which is going to be discussed here is sintering. The compaction and sintering of high temperature materials may also be studied by TMA. So figure shows the sintering of a refractory clay block under conditions designed to reproduce industrial furnaces. So here is the TMA curve for refractory clay, and actually if we see it quite carefully, so there are two curves here. So first one is TMA curve. So if you follow the pointer, so I'm going to show you the TMA curve. So this one is the TMA curve, you can see here. This one is the TMA curve for refractory clay, and then there is another curve, and that is the derivative TMA. So here is the derivative TMA curve, so you follow the pointer. So derivative TMA. So this derivative TMA actually it gives us a lot of information about the changes which are going to be happen in refractory clay. So if we see the curve derivative TMA, so we see that there is a slight change or very little negligible change up to the temperature of 900 degrees centigrade, and then there comes the dip, and this dip, this actually shows the shrinkage in the sample. So that occurs about 980 degrees centigrade, and if we talk about more precisely, so that this occurs around 978.2 degrees centigrade, and the shrinkage which has been calculated over here, that has been observed as 2.7%. Then we can see here another dip over here, which is going to be happen between 1100 to 1600 degrees centigrade, and shrinkage which was observed over here was 23.6%. And the last application is the polymer cure. So by using TMA technique, we can calculate the extent of cross-linking present in any polymer. So there are several ways of using TMA to study polymer cure. If the effect of cure on the glass transition temperatures has already been established, TMA could be used to measure glass transition temperature after various cure times. As the polymer cross-links, as the cross-linking starts being generated in polymer, then at a certain conversion it forms a gel or network structure. So means the polymer is being converted into gel-like shape, and then the viscosity of the polymer rises considerably at this stage. The gel time means the time at which there is gel-like appearance of the polymer starts. So this gel time can be calculated using dynamic load technique, that is DLTMA. And with the resin contained in a suitable container held isothermally, the probe force is changed, that may be changed around minus 0.05 to plus 0.05 Newton. Before the resin gels, means before the gel-like appearance starts to appear, the probe oscillations has been observed to be very much large. Before the gel-like appearance, the probe oscillate quite much freely, and when the gel-like appearance starts, when the cross-linking starts in the polymer, its viscosity suddenly increases, and the probe can no longer oscillate now freely. Then using the parallel plate rheometer attachment, the gel time of pre-preg material, which is a kind of a fabric, has been investigated. So here is the TMA curve, which is actually the gel time of pre-preg using the 5 layers in these conditions. So here is the time on this axis, then here is the dimension, and here is temperature. And this curve actually it shows the cross-linking, which is going to be increased with the passage of time, and this is the curve for pre-preg actually. So when heated at the rate of 10 Kelvin per minute, the material first expands slightly, so we are talking about this one, and then it softens at about 70 degrees centigrade. So here the softening process starts over here, and eventually after around 8 minutes at about 85 degrees centigrade, gelation occurs. So here the gelation process starts. So at this time period, the probe oscillates quite freely, then the oscillation goes on slow down, and then gelation process start, and now the oscillation of probe ultimately stop over here. So dear students, this is all about the applications of thermomechanical analysis. Hope you do understand it. Thanks for watching, and if you like my video, then like it, and if you didn't subscribe my channel yet, then subscribe it right now to get in touch with my upcoming videos. So thanks for watching. Thank you very much.